Hi Grace, Mr. Shaw here. Thanks for those questions. Here are the answers, my friend. Chapter 4 review, question 13E. So having done the first, I'm assuming you've done 13A, B, C, and D, and you've already found the answers. So this is what you already know. All right. So here's the circuit. 3 resistors in parallel, 120 volt battery. You've already figured out that the total resistance is 60 ohms. The total current, the current that's coming out of the battery, is 2 amps, and the current in each of those resistors is 1.2, 0.6, and 0.2, and that the power output is 120 times the 2 amps, which comes to 240 watts. So you already know that by the time you do part E. And question E says, how much total power is consumed by all of the resistors? 240 watts is coming out of here. How much of it gets used by all of those? And the answer is all of it. This is almost a conservation of energy question, right? Way back in about year 8, we told you that energy can't be created or destroyed. It can only be changed into certain types. And power is just how fast energy gets used. It's energy divided by time. Right? It's so voltage in particular is how many joules each coulomb is. Is how many joules each coulomb is carrying with it. So if the energy into the circuit equals the energy out of the circuit, and that's not changing, then the power into the circuit has to equal the power out of the circuit. And that's the short way to answer this question, right? You just say power supplied has to equal the power used, and therefore it equals 240 watts. So these guys have to use 240 watts because that's what was supplied. Another way to do it, another way to calculate it, is to calculate P equals VI for the parallel section, for this as a whole, not for one of them and then the other. You can do that. You can go P equals VI for each of these 3 and then add it up, but it's just 3 times as much work. You can do it for this. Right? The voltage drop from there to there across the whole thing has to be 120 volts. Because again, 120 volts is supplied, so it all has to get used. Right? So as the electrons come around, they've still got 120 there. The only place they're going to get used is in these resistors. So from there to there, that's where it all gets used. Nothing around here to use power. So all of the volts, 120 volts, are going to get used there. And the total current through this thing is the 2 amps. Right? It splits 3 ways, but if you add it all up, it's 2 amps. So again, whenever you use power equals VI or V equals IR, you have to make sure that all of these things are talking about the same place. We're talking about all of that. Right? So it's 120 volts, 2 amps, 240 watts. So either way, you're going to get the right answer. Right? So that's 13. Now, 17. This is a genuinely tough question. This is a really difficult question. It's a little bit complex mathematically too. So here's how it goes. Now the question says, we've got a section of the circuit like this, 3 100 ohm resistors. Each of them can only dissipate or use 25 watts of power at the most. Right? Now this one is going to use more power than those 2 because this one gets all of the current and these guys get half of the current each. Right? So no matter how much power this one is using, these guys are going to be using less power. Right? So the question says each resistor can take a maximum of 25 watts, right? And they're not allowed to have any more. So we know that it's going to be maxed out when this one's taking 25 watts. If we let these guys get up to 25 watts, that only means that this one's got even more power going through it, and that's too much for it. So this is the starting point. We're going to start by assuming that at the maximum for this whole circuit, this one is right on 25 watts. Right? So let me put this to work for you. Okay. Sorry, I just have to grab something. Right. So the 2 formulas we've got to use here, or that we can use here, are V equals IR and P equals VI. Now I'm going to find current first because I haven't got anything about current here, and both of those have got I in it. So somehow I'm going to need to get current. I'll need to find out how much current can go through there when that's happening, when the 25 watts is happening, and that will help me find information about here and here because I know that I'm going to use something that's got I in it, and I'm missing that at the moment, so that's where I'm going to start. So I'm going to tell myself what I'm doing. I'm going to find the current in R1, that one. Okay. So P equals VI. Let's see. And this is the hard part, right? Because you're going to use both of these and you end up doing simultaneous equations. So look forward to the maths here. So here's what happens. So P equals VI, and we know what the P is. It's 25. At its maximum, 25 equals, we don't know the voltage, excuse me. We don't know the voltage across there. We don't know the current through it, so it's just VI at the moment. This, the only thing we know out of this, we don't know the V, don't know the I, we know the resistance, 100. Right? So from this one, you get V equals I times 100. I'm going to write it as 100I. Now I'm hoping you've done simultaneous equations before. You should have. So I'm going to call that equation 1 and that equation 2. And you substitute one of them into the other one. Instead of writing V there, because this is V, V equals this, I can just write that instead of V, and that's what I'm going to do. So I'm going to substitute number 2 into equation 1. So this is what you get. You rewrite equation 1, 25 equals V, which is that, times I, okay, which is 100I squared. So I'm going to juggle that around. Therefore, I squared equals 100 divided by 25. Therefore, I equals the square root of that. I'm sorry, I did that upside down. It's 25 over 100, which is 0.25. Therefore, I is the square root of that, which is 0.5. So when, we've just found out a key thing here, when this resistor is maxed out, getting its total amount of power, it's got half an amp of current going through it. That's important. Okay, next thing. We can now find the voltage going across this. So again, say what you're doing. Voltage in R1. This is a very big question. It's easy to get lost. Okay, and again, we're talking about R1. So we're not talking about the whole thing or anything over here. We're just talking about this. All right. So the resistance in this is what we're going to use. So the R is 100. The I through there is 0.5. V equals IR, which is 0.5, whoops, times 100, 50 volts. Now the question said, when this is maxed out, how much voltage can happen across there? What's the biggest potential difference from A to B? We've just found the potential difference across this part. So we're halfway there. All we need to do now is find it across here, add the two together, and we're done. We're still a fair way to go. All right. Let me just separate all this out a little bit. Again, organize your work. In a big problem, you need to know where you're going. All right, part 3. I'm going to find the voltage across R2 and R3. Now keep in mind it's going to be the same. That's one of the things about parallel circuits. The voltage drop, the potential difference from there to there is going to be the same as from there to there, right? Because the potential difference, the voltage that something has there is the same as the voltage that something has there. And the voltage that something has there is the same that they have there because nothing's been using it, right? And from there to there is going to be the same whether you go this way or whether you go that way. So in parallel circuits, the voltage drop across one is the same as across the other. So I don't have to do it twice, I just have to do it once. Okay. Find the voltage across these guys. Now the current through there will be halved. They are equal. They're 100 ohms each. We've got half an amp coming through here, and exactly half of that is going to go through there, and half of that is going to go through there. Sorry, it just started raining outside. I thought I'd get rid of the background noise. Okay, so straight away you can say I in R2 is going to be half of I in R1. So just explain yourself. Therefore, I for this bit is going to be 0.25 amps. Pardon me. And the resistance is 100 because they're all 100, and we're trying to find V. Right? Write these headings. You remind yourself what you're doing. V equals IR 0.25 times 100, 25 volts. Okay. Then you can say, therefore, the voltage across R3 is 25 volts as well. Okay, finally we can answer the question. So the voltage across A to B, or just across AB, is the two answers added together. So as electricity goes from there to there, it loses 50 volts of potential difference through there. We just found that out down here. And having lost 50, we've now just found out that it's going to lose, whichever way it goes, it's going to lose another 25 when it goes through either one of these. So from A to B, it's lost 75. So you just have to say voltage from A to B is 50 plus 25, 75 volts. That was difficult. That's about as hard as they get. Part B. How much power is dissipated by the circuit now? Okay, so having done that, now that we know how much voltage is across each one and how much current is going through each one, we're just going to do P equals VI for each of them. Right? So for resistor 1, resistor 2, resistor 3, they're all the same. Power equals VI. Same thing, which equals, for R1, voltage in R1 was 50. Current through R1 was 0.5, right? These headings tell you things. Speeds things up. So that's 25 watts, half of 50. For each of the other two, the two numbers, voltage is 25. Current was 0.25. And that comes to 6 1/4. Same thing. Right, so having shown you that, I've just written this down here. Okay, VI for the first one, 50 times a half, 25. VI for the second and the third is the same for both. 25 volts, 1/4 of an amp, 6.25 watts. So the total is you just add up those three answers. Right? And that comes to 37.5 watts. That's how to do question 17. That is one tricky question. Okay, 19. Now this says, why is the shock received when a finger touches a live wire likely to be less severe than the shock received by a person who touches a live wire with a pair of uninsulated pliers? It's all about how big the contact area is. If I touch a wire with my finger, right, there's a very small area of contact there. I'm just going to get a blank piece of paper here. Right? There's a very small area of contact there right at the tip of my finger. So my fingertip has a reasonable amount of resistance. Only a certain amount of electricity can get into my body through that little tiny door at once. Right? But if I'm touching it with something that conducts electricity really well, like a pair of pliers, which are made of metal, and the area that I'm touching the pair of pliers with is my entire hand, then electricity is going to race into my body. Right? It's going to treat the pliers just like a big fat wire, right? So I haven't been electrocuted yet. But if I'm touching the handles of a pair of pliers like that, right, then the electricity can race into my body through a great big area, the size of my hand. Now the other problem about it is, of course, if I'm holding onto the pliers, electricity can take over your nerves and can force me to keep on grabbing the pliers, and I cannot let go. So it's dangerous for two reasons. The main answer to the question is it's all about surface area. This way, only a small amount of electricity can go through at once, and so not much will. And if I'm grabbing something that's conducting electricity with my whole hand, more electricity can go through me at once. The fact that I'm going to grab it harder only makes things worse. That's question 19. Now 20. I've written this down here so you can have a look at it later on if you need to. Pardon me. Okay, difference between a fuse and an RCD, a residual current device. Okay, a fuse is a little thin piece of wire that is at the sort of entrance to your house's electricity supply. All of the electricity that goes into your house goes through one spot first. There's literally a front door for you and a front door for electricity. And in that front door, we used to have fuses. The fuses were a tiny, thin piece of wire. If most of the wire that electricity goes through in your house is that fat, the fuse was very, very thin. Right? And all of the electricity had to get through this tiny fuse at once to go into your home. And if too much electricity was getting sucked into your home because you had too many things turned on, you had a toaster and the heater and the oven and all that sort of stuff on at once, and someone turned the shower on, right, then so much current would be trying to get through that thin wire that it would break, it would melt. And that would stop all of the electricity from getting into the house. If it didn't happen, if that wasn't there, and if there was no limit to how much current could get into the house, then you could conceivably turn so much on in your house that you'd melt these wires, and these wires are inside your house where the heat from the melted wires can start a fire. And houses have been burnt down. A great many thousands of houses have been burnt down in the distant past because we didn't have fuses, and it took us a long time to work out what was going wrong. So these are a good thing. What they don't do is they don't measure the current going out, because keep in mind that the electricity that goes into your house is just part of a bigger circuit that started at the power station. So this goes into your house. There's a house. And it has to come out of the house from another wire. This is why when you look up at the power lines, there are two wires. There's one bringing the electricity to you, and there's one taking away from you. So there's electricity going in, and then it has to go out. Now these things are fantastic at protecting property, because too much electricity going in might set the house on fire. But there's another issue. If there are, let's say, 10 amps of electricity going in, then there really should be 10 amps of electricity coming out. Even though all of this is a lot more complex than what I've drawn here, even though this branches out into different rooms and different power points and lights and all that sort of stuff. It's a very complex circuit inside your house, but there's one way in and one way out. So the amount of electricity that's going in should be exactly the same as the amount of electricity coming out all the time. It should never deviate. And the only reason it's likely to change, the only reason that might be 10 amps and this might be 7 amps, is if the other 3 missing amps are actually going through you and electrocuting you at the time, right? So 10 amps normally goes in, powers the toaster or whatever, and then goes back out again, right? So if these aren't the same, it could be, and it normally is, because something has gone horribly wrong and somebody might be getting electrocuted. So the other 3 amps might be going through somebody's body to the ground, and that's killing them. And that's where this comes in. A residual current device. Firstly, it does do what a fuse does as well, right? It measures the current coming in, and if it's too big, cuts off the electricity. So it still protects the house. But as well as that, it measures the current going out as well and compares the two. And if there's a difference, there shouldn't be a difference. If there's a difference, it also cuts off the electricity to the house. Because if there's a difference, it's likely that somebody's getting electrocuted or is about to. So instead of getting electrocuted for minutes and dying, you might get electrocuted for a tenth of a second or a fifth of a second. You get a very quick, sharp jolt and it's over before you know it, and it hurts, but you live. So that's what an RCD does. Okay, Grace, there are the answers. Thanks very much. Write back to me if you still have more questions about that. Otherwise, I'll assume everything's fine. Bye.